And the sort was all about the difference between all of the rational and irrational numbers. So give me an example of an irrational solution. Y squared of 20. It's not a perfect square. There's a perfect square in it, square root of 4, right? So that'd be 2 square root of 5 if it was reduced, but it's still irrational. What would a rational solution be? Does anybody know? Okay, so that'd be 4. What about 2/3? Is that rational or irrational? It's rational, good. So you could have a hit on the x-axis at 2/3, but like yesterday when we worked with those quadratic questions, you could get an irrational that looked like this. Those could be irrational solutions that are generated from using the quadratic formula. Remember question 42 in the homework last night? Were any of those perfect rational solutions? No, every single one of them hit between two integers somewhere, and they never ended and never repeated, which makes them irrational solutions. Even though 0.5 is a decimal, why is it rational? When you divide it out, you can write it as a fraction. So make sure you don't just throw all decimals in the irrational category. If it ends like 0.275, that would be rational. It's a decimal, yes, but it's still rational because it ends. All right, things you will need to be able to describe from a function. First, I'm going to give you a picture. So as closely as possible, copy the following picture. As closely as you possibly can, and we're going to add some more vocabulary. Let's start with something that's review. In behavior of this function. As this function heads the y's in the negative direction, so as f of x goes towards negative infinity, remember f of x is the same as saying y. As f of x or y goes to negative infinity, then what does x do? Careful. As the y goes negative, what is the x doing? It's going what? Negative this time. Negative infinity. How do we usually talk about it? We usually say the x is first, but our book and what you're going to do in calculus later is going to require you that you talk about the y first. So I have y is going to negative infinity as x is going to negative infinity. Now let's talk about the other end's behavior. As y goes to positive infinity, as f of x goes into the positive y's, then, bless you, then what is x doing in this situation? As y goes positive, what is x doing? Positive this time. And remember that it doesn't always work that way. Sometimes the signs are flipped. As y goes to the negative, x goes to the positive. That is in behavior. That's how you describe it. That is the exact notation you will use on the test. In behavior is how does it act in the long run. Not what happens in this little space between this part, but how does it act in the long run. All right, the next vocabulary word we need to talk about is, what do we call this highest point? Highest point, because it's not really the highest point, right? Because the highest point is way out here somewhere that never ends and we're never going to get there. So we call this a local maximum. A local maximum. It's localized just right, just right here in the middle of the function, middle of the graph, we have a local max. Where would you say the local max is located? What's its position? Good, negative 1.53. You could always call that a relative max. You will hear both types of vocabulary, a local max or a relative max. It's localized here in the center, or it's relative to the fact that you're not discussing how it does in the long run, that it's relative to what's going on just here in the middle. All right, do you have what you would call a local min? What do y'all think? What do you think it is? 2.0? Uh-huh. Yeah. Yes, because what could a graph look like, Tate? Good question. Couldn't a, whoops, what would help if I showed it to you? Couldn't a graph do this? So couldn't there be two local maxes and a local min and a local min? There could be a lot of stuff going on. And this is what a calculus function is going to look like when you get to AP Calculus. Goofy like that, like a whole bunch of stuff going on. So good question. Yeah. All right, so now, do we have a lowest point that's not talking about in behavior? Do we have a lowest point? What do y'all think? I kind of already answered it. 2.0. You can call it a local min, or you can call it a relative min. There is no min. So when you say a relative min, it just means relative, that you're not talking about what happens in the end behavior. Whereas its location here at 2.0, it almost looks like that little part is a parabola opening up, and it almost looks like that part is a parabola opening down. But indeed, it is not. Do you know what it's called when one arm's up and one arm's down? What? Could be a cubic, could be a fifth-it, could be a seventh-it, it could be a ninth-it. How do I know that? Because it's odd. Good. One arm up, one arm down. It has to be an odd. This particular one is a cubic. Harrison's right. What are the solutions? And be very careful here. What are the solutions? Go ahead, Harrison. Okay, I agree with x equals negative 3. What else did you say? Selena, what's he left out? You asked about it in the homework. Where's the double root? How did you know it was on the 2 and not the negative 3? If it is tangent to it, turns and goes back up. From the solutions, which was homework last night, could you create the polynomial function? I have a few nods in the room. What would you have to change all the solutions to? What's the word? Factors, okay? And this test is so heavy on vocabulary. You have to know what each vocabulary word means. Your solutions double as your x-intercepts in this case. Can you tell me where the, I didn't make it very clear, where the y-intercept would be? What'd you say? Around 2. How would you write that as an ordered pair? Y-intercept would be what? I hear 2, but it's not. There you go. I heard the 2 part. It has to be written as an ordered pair when you say it's a y-intercept. You can't just say y-intercept 2. Always make sure it either says y equals 2 or the ordered pair. Anything else you know about this graph that you could tell me? We said it was odd. We figured out it was cubic by the roots. We found the local min, local max. Found the x-intercepts, the y-intercepts. We changed the x-intercepts into factors. Anything else that you could tell me about this graph? Because that is a lot of stuff you've learned in less than 6 months. You can say a lot about that graph in less than 6 months. Some of it you knew before, but some of it we've added since August. All right, let's figure out the polynomial, actual polynomial function that it is. So how am I going to do that? Help me, Britta. What would I do with the factors to get a polynomial? How? And then what do I do with them? How many at a time? Perfect. One thing you must know is the leading coefficient is 1. All right, we're not working with anything yet that doesn't have a leading coefficient of 1. All right, so Britta said 2 of them together first. So I would say x squared, 3x minus 2x is 1x, then minus 6. So that's my trinomial that has to be times a binomial. The question was asked this morning, do you have to use the box method? No. Some of you were not being successful in the test, so I suggested strongly that you try a different method, which might be the box method just because you weren't getting them correct. You do not ever have to use, unless I specifically say. The way I do it is never the only way to do it. All right, combine like terms, x cubed, negative 1x squared, negative 8x plus 12. If you graph that polynomial function, anybody need more time to write that down? All right. We started with vocabulary. We had an example 1, example 2. G of x equals 2 times the quantity x minus 1 squared times x minus 4. What do you know about this function just from that? You have no graph. What do you know about it? What are the x-intercepts? What do you do with the factors to get x-intercepts? Harrison thinks he knows. Does anybody else think they know what to do with the factors to get x-intercepts? 2 people? Anybody else? Blake, do you know? No? If it's already in factored form, what would you do, Harrison? Yeah, perfect. Take each one of those, x minus 1, set it equal to 0, x minus 4, set it equal to 0, x equals 1, x equals 4. So I have x-intercepts at 1, 0, 4, 0. Why do I know from just that much that I have a double root? You know, from the equation, why there's a double root? Because the what? No, but you're warm. The 2 is the leading coefficient. That tells us whether it opens up or down. Hannah? Yes, yes. And you figured that out before I was even finished talking. The x minus 1 quantity squared tells you that there's really what? How many of these x minus 1s? 2 of them. Now what this tells you is it's a vertical stretch, double, and it tells you that it opens the normal way of a cubic. What if it were -2? Then it would tell you that the arm goes up first instead of down first. All right, we know the x-intercept. Could you get the y-intercept? How? On the y-intercept, what do you have to let x be? 0. So where would you end up? You'd end up at 1 times -4. Is that where you'd end up? 0 minus 1. -1 times -1 is 1. Times -4 is -4 times 2 is, I'm thinking -8. I wrote down +8 though. I'm just going to work it out. Y-intercept. To get your y-intercept, your x has to be 0. Yeah, I'm thinking it's -8. So that means it's 0, -8. So those things you know from not seeing the graph, just seeing your equation. Let's see. Double root at 1, 0. Okay. Then we have at 4, 0 a pass-through root. And then at 0, -8, we have a y-intercept. So to make this function work, even though I don't know the relative min or relative max, oh, I kind of do know the relative, no, I don't. Yes, I do. I do know the relative max, because there's a double root where. So when I come up out of this problem, what has to happen at this point right here? Yeah. And then it's going to go back up like this. Now, I did not know anything about that graph except that much. Why is it a sketch instead of a graph? Why are we calling this a sketch instead of a graph? Yeah, we're just guessing at where, knowing the y-intercept, a double root at 1, 0 and 4, 0, we are getting a pretty good guess. What is the point that we need? Because we definitely know the relative max, because of the double root, is at 1, 0. How could we get the relative min? It's not given. All right, not given. Say that again, Harrison. See where it's the lowest. It's probably because it's between 1 and 4 that it's probably going to be right there where you're talking about in the 2, 3 on the x range. Let's clear this out. You don't have to FOIL it out to put in your calculator. You can just put it in exactly like it is in factored form. The calculator doesn't mind. 2 times x minus 1 quantity squared times x minus 4 were we pretty close in our drawing. Second trace, we want a minimum this time. So second trace, go to number 3, press enter. You want to be just left of the minimum, press enter. Then it asks you in the text message, are you right of it? No, I have to hit the right arrow key till I'm right of the minimum, press enter. Yes, I'm ready to guess. It is at 3, -8. So we went to y equals, and we put in our function, g of x. We then went to Zoom 6, for people who are absent, I'm writing this down, Zoom 6. Then we went to second trace, and we chose minimum, number 3. You have to then be left and press enter. You have to then be right of the minimum, press enter, and then guess enter. So the only reason I'm writing that out, nobody's absent in this class, but I use the same notes for 6 periods, so that way they will know this is how we got our relative min. Everything else came from just the equation. Nothing else, just the equation. All right, I went back and labeled this lesson 5.8. Sorry, I did not put that at the top. Does anybody need more time on this graphing business? Will somebody jump to page 390 real quick? Who has their book with them? Does Dylan have his book today? Tell me what the directions are, Dylan, on page 390 for number 15 through 20.
Estimate the coordinates of each turning point and state whether each corresponds to the local maximum or local minimum. Then estimate all real zeros and determine the least degree.
The least, it said?
Yeah.
All right, so here are the directions. Under each one of these, you're going to list max, min, zeros in this order, because that's how we're going to check them, and the least degree that the polynomial could be. So that means if there's 3 zeros, then it's a least 3 term polynomial. It could be, you know, double roots of things or whatever. Look how the answers are, because this is the way I want you to do it. You get your graphing calculator. You write down max, min, zeros, least degree it could be. You estimate these, okay, and your least degree is looking at the graph. If it was odd and it has one arm up, one arm down, and it has 3 zeros, then what's the least it can be? A 3. Could it be a 5? Could it be a 7? Potentially, yes. Okay. You're not telling how many zeros there are. It's the least degree that your polynomial would have. So you want max, min, zeros, least degree in that order written on your paper. You should be able to get these 6 problems done. We're doing 15, 16, 17, 18, 19, and 20 before you leave here today, because you do need a graphing calculator. And remember, it's not the real max, it's the relative max or the relative min. Hold on just a second, Wes. Sit down. Yesterday, I had to clean up back there. Why? Why was it a mess? Because the